Today we start a series of videos, Unit 3, on atoms. It's kind of a history lesson, really, in how we've come to the understanding that everything is made of these little bitty particles. Atoms are a really fundamental part of chemistry, and you can't really understand chemistry without understanding this atomic theory. But I don't really want to just tell you atoms are there and hope you believe it. I would rather support what I say by giving you some evidence, some historical reasons to believe that atoms exist. To go back as far as we can to start telling this story, we have to look for one of the first times that we had a group of people that had enough peace and prosperity that they could worry about such silly things as what matter is made of and record it for us. And that group of people was the Greeks. The Greeks gave us the first kind of recorded evidence of somebody thinking about what matter was made of. And we're going to take a look at two different guys, Democritus and Aristotle. They're both Greeks. They didn't live exactly at the same time period, but close, and they had two different ideas. Aristotle believed everything was made up of four elements. He didn't make any distinction between matter and energy. And the elements were earth, wind, fire, and water. And since everything is a combination of these elements, when something appeared to undergo a change, what was happening was, in Aristotle's mind, it was just changing its composition. For example, an olive tree that was growing on a still day might look like this. It has a lot of earth. Plants and things attached to the earth were considered to be largely earth. And water, because it's wet. If you cut the bark off of a tree and feel inside, it's wet, so there would be water there. That same tree, in a summer breeze, now we notice that it's got not only earth and water, but it has acquired the element wind. You know, we don't think about that event that same way. We see the leaves rustling in an olive tree, we think, oh yeah, the wind is blowing through the tree. Not that the wind has become part of the tree, but that wasn't Aristotle's idea. In a thunderstorm, well, the composition changes even more. So now we've got more wind because it's windier out, and it's wet on the outside as well as the inside because it's raining, so it has acquired more water. Not that the water came from outside and coated the tree, not that the wind blew through the leaves of the tree, but the wind and the water became part of the tree. Here's the olive tree when a lightning strike happens. There's a flash of fire. Suddenly it acquires fire, and then it loses the fire. Tree is cut down and it dries out. Wind disappears, some of the earth is gone because it gets lighter, the water all is gone, so it's changed its composition again. Then the dried out tree is thrown into the fire, loses all the earth, gains some fire, and then eventually even the fire goes away. Well, obviously that's a very different way of looking at matter than what we have today. So how did we get from there to where we are now? Actually, it took a while. Democritus, who we're going to talk about, had a different idea, and it's closer to what we think now, but it didn't catch on at first. And in fact, we went through the entire period of the Middle Ages mostly buying into Aristotle's idea of four elements. Democritus is the second Greek who left us a recorded different idea of what matter is like. He didn't buy into the whole elements thing. Democritus thought that there was just one stuff. There weren't four elements, there was just one thing. And everything was made of little tiny bits called atomos, or we would call them atoms in our language. Here are the characteristics of Democritus atomos. One is they're too small to see. They're invisibly small. But we can understand something about them by watching how they behave. They're indivisible, which means you can't break them up into anything smaller. And this is where Democritus and Lucretius, who was kind of his colleague, first came up with this idea. They thought about if you took a vase, let's say, it's a piece of pottery, and you smash it with a hammer, and you took one of the pieces and you smashed that, you'd get smaller pieces. And if you took one of those small pieces and hit it with a hammer, you'd get smaller pieces. But you could keep doing that for a while, and eventually you'd come to the point where you'd have a piece so small that you couldn't smash it anymore. And that would have to be an atomos, an atom. Another characteristic of these atoms is they have different shapes, and that's how Democritus and Lucretius explained how different kinds of matter behaved. For example, liquid atoms, well, they thought that their characteristic would be that they had these circular shapes. Lucretius, in a big long poem called On the Nature of Things, he described liquid atoms as being like poppy seeds in your hand. So if you had a handful of poppy seeds and you move your hand around, those poppy seeds would flow around like these atoms. Because of their circular nature, they behaved the way they do, and that would explain why liquids existed. Solid atoms had these little hooks, almost like Velcro sort of. And so the atomos would hook into each other, and so when you pull on one side of a piece of metal, let's say, and pull on the other side, the hooks all hook together and they pull back. And no other form of matter did that, and so that was his explanation for this behavior. Gas atoms, well, they didn't recognize something like air as being a gas, but they knew there were things that were invisible that were in the air that had to be matter. And you could smell them, like a strong-smelling perfume or some ammonia or a sharp onion smell. So they thought those things are poking you microscopically somehow in your nose and causing some kind of a sensation. And so they had the idea that gas atoms are pointy and kind of like little arrows jabbing you, like we see here. Well, as I said, Aristotle's view of matter was the dominant view throughout the Middle Ages and into the Renaissance period. And it wasn't until this person here, Antoine Lavoisier, a French scientist, came along that things really changed. Lavoisier is often considered the father of chemistry. He was the first person who really started thinking about matter as being made of what we now believe elements are, the modern idea of elements. So he discarded the Greek ideas, Lavoisier did, and he redefined elements in much the way that we think about elements today. We're going to look at two statements that will define what we think an element is now. Lavoisier says, an element can't be produced from another substance unless another product is also formed. If I produce an element, I'm going to call E my element, from substance A, let's say, I will also have to produce another product, which I'll call substance B. In other words, I can't do this. I can't say A turns directly into E. I can't change lead into gold if both of them are elements. And another way of looking at this is no substance can be produced from an element without adding another substance. So if I start out with an element, E, and I'm going to turn it into some other substance, which I'll call B, I cannot do that unless I add a third substance to the element. Elements in both of these examples have this characteristic. There's something that you can't change them into anything else, and you can't change anything else into them. Elements are immutable. They're unchangeable. And this was a sort of a problem for the early chemists of that period. They're called alchemists. Their big goal was to change, actually, lead into gold, or iron into gold, something cheap into something expensive. And they thought they could somehow do it. And Lavoisier's understanding of matter was deep enough that he was able to show that that couldn't ever happen. And so people had to start thinking about a different way to get rich. Another contribution that Lavoisier gave us was a naming system, and we still use this naming system. We actually understand more about how it works than Lavoisier did at the time, but he laid the groundwork. In the past, everything had a common name, or what we would call a trivial name today, like wood alcohol, for example, or table salt, or Epsom salts. And those names were derived, a lot of those names were derived from where they were found or what they were used for, but it didn't really give anybody an idea of what they were made of. And Lavoisier said, if we're going to have this new science that proposes that everything is made up of a small number of elements, we should have a naming system that tells us what elements are there, what elements are present, and then also what are the relative amounts of each element that are present in the compound. So instead of calling something water, we would call it dihydrogen monoxide, H2O, which would give us an indication that it's made of hydrogen and oxygen, and there's twice as much hydrogen as there is oxygen. Lavoisier didn't have that sophisticated of a understanding that he could have come up with a formula like H2O, but he did lay the groundwork that we should name things out of what they're made of. Now, sometime after Lavoisier, people started doing a lot of experiments, taking compounds and tearing them apart and weighing what came out of there, weighing the elements that were produced. And two mysteries developed that nobody had an answer for. The first one is called the law of definite proportions. The law of definite proportions says the ratio of the masses of the elements in a compound is always the same, no matter how big or small of a sample you use. As long as it's the same compound, you take it apart into its elements, weigh the elements, you're going to get a ratio of mass to mass that's always going to be the same. For example, this is compound A, made of sulfur and oxygen. And I'm not giving you the name of this thing, I'm just saying that it's a compound that's made of sulfur and oxygen. In the first sample that we have, which is 100 grams big, 50.02 grams of it is sulfur, 49.98 grams are oxygen. What I want to do is get a sulfur to oxygen mass ratio. So for this first compound, I'm going to take the 50.02 and I'm going to divide it by 49.98. And the answer I get is 1.0008. So if I'm going to round that off to 4 significant figures, I would come up with a ratio of 1.001. Now let's do the second sample. It's smaller than the other one. It's only 23.720 grams, but let's find the mass of sulfur to oxygen. So 11.865 divided by 11.855, and my answer is 1.0008. I have more significant figures here, but if I were to round it off to the same number of sig figs in the last one, I'd have the same number. So they're very similar. Let's do the third one. This is a much smaller sample than the other two. It's only measured in milligrams instead of grams. Let's find the ratio of sulfur mass to oxygen mass. 15.1 divided by 15.0. And here I have only 3 significant figures, but it's 1.01. So in all 3 of these cases, we find that the sulfur to oxygen mass ratio is very similar. It's about 1. Now, it turned out that if you did 100 samples or 1,000 samples of this, you'd always get that same ratio. And it didn't matter which compound that you picked, each one would have its own different ratio, but it would be consistent every sample that you used of that compound. Nobody had a reason that this would be, but it certainly seemed to be something built into how matter was. A second mystery was the law of multiple proportions. Now this one's a little bit harder to get, and its definition is a little more wordy, but it's actually a much more important and mysterious dilemma. People realized that there was more than one compound that would contain the same elements. Like, for example, carbon dioxide and carbon monoxide. These both contain carbon and oxygen, but they're slightly different compounds. Or water and hydrogen peroxide. They're made of both hydrogen and oxygen, but they're not the same compound. So if you did this definite proportions thing for 2 different compounds, found out what their ratio of one element to the other was, and then you took the ratio of those ratios, you found out that you'd always have a small whole number ratio, a simple 4th grader fraction, like 3/4 or 2/3 or 2 or 1/2. So those things just kept popping up over and over and over and over again. And it just seemed like too much of a coincidence to let it go, but nobody had a good explanation for it. Like, here's an example for the law of multiple proportions. Compound A that we just looked at, well, the sulfur to oxygen mass ratio that we found was 1.001. But here's a different compound, compound B, that also is made up of sulfur and oxygen. Let's find out what its sulfur to oxygen mass ratio is. So I'll take 40.08 grams of sulfur and divide by 59.92 grams to get my ratio, and it works out to 0.6689. That's my ratio. Okay, so here's the definite proportion for one compound. Here's the definite proportion for the second compound. If I take the ratio of definite proportions to each other, like 1.001 divided by 0.6689, I would get a small whole number ratio. Let's see if it works. So I'm going to take 1.001 and I'm going to divide by 0.6689. And here's what I come up with. To 4 significant figures, I get 1.496. But 1.496 is really, really close to a small whole number ratio. 1.5 or 3/2. And if I had chosen to do B over A, well, I'd have just gotten 2/3. So it didn't matter how these people analyzed it. When they came up with these ratios, they always turned out to be small whole number ratios if you had two different compounds made of the same elements. That was a law. It was because it happened all the time, but it was a law without a theory. Nobody had an explanation for why it would be. They just knew that it was happening. So, next video, we're going to take a look at an unlikely hero. One of the most important discoveries in science was made by a high school teacher who explained this whole thing.